Next section, 7.3, is trig substitutions. These substitutions, to date at least, are the most complex, involved, and perhaps outright tricky of the integrations we've had to do. Now, some of this stuff we're going to learn by rule, but and so you need to make some flashcards, but it's just intrinsically a difficult area. Now, when do these trig substitutions come up? Well, in the simplest cases, we're going to have things that look something like this: a squared minus x squared, or square root of a squared plus x squared, or square root of x squared minus a squared. Something of this form, or something that when you complete the square you could make look like this. And in these situations you can do a trig substitution. What we're basically trying to do, and what it's going to allow us to do, is get rid of this square root sign. That's going to make it a lot easier to solve the problem. Okay, so we've got to make our substitutions. In situations that look like this, we're going to say x is equal to a sine of theta. And in situations where we see this, substitution that we're going to make is x is equal to a tangent theta. And finally, in this situation, we have x is equal to, or x will be substituted by a secant of theta. You need to make note cards and you need to memorize this, but let's just for a second discuss kind of why is this true. And I think this is the most intuitive case, although we could easily explain both these cases. And if you look at page 461, you'll see an explanation for each of them. But let's just talk about this central one. Look at this: square root of x squared plus, of a squared plus x. Well, obviously one way to think about that is the Pythagorean theorem, right? That is going to be the length of a hypotenuse of a triangle. And we can then say, well, this is x, this is a, and then this over here is going to be the square root of x squared plus, a squared plus x squared. And let's make this the angle theta now and see what happens. Then we have a situation where we're going to say x is equal to a times tangent of theta. Well, let's just write that out down here, over here. X we claim is equal to a tangent of theta. Well, what is tangent of theta? Well, that is going to be the opposite over the adjacent. So we claim x is equal to a times the opposite over the adjacent. This cancels with this. X is equal to x. Hey, this worked out. And in fact, if we look at each of these cases, it's exactly the same. We can make our little triangle, and we find out this substitution actually isn't like a rabbit pulled out of a hat. It does make sense in terms of the trigonometry of what's going on. Okay, so you're convinced that we can do this, but that means now that we can rewrite this as the square root of a squared plus, now we do our substitution and we get the quantity a tangent theta squared. But one of the things I said was we were going to be able to get rid of this square root sign, and so far that hasn't happened. What we now have to do is resort to a little algebra. So let's multiply this out, and we get a squared plus a squared tangent squared of theta. Factor out an a squared, and we get a squared 1 plus tangent squared theta. hopefully you begin to see where I'm going here. Obviously now this a squared can come out. We get a times the square root of 1 plus tangent squared theta. You remember from your trig identities that 1 plus tangent squared theta is secant squared theta. So now we get a square root of secant squared theta, and obviously that's equal to a times the absolute value of secant theta. And you notice that that last step we were able to get rid of the square root sign. That was the trick. That's what we wanted to do, and we wind up with this value coming from up here. So in a way, this is the substitution that we made, but then we wound up, after we did our algebra down here, with this. And this is going to be far easier to integrate than the original term. And we'll have to work some examples to kind of show how this is going to happen.